Welcome to G Fun Facts Online. The sight of a bridge collapsing is a nightmare scenario. These massive structures are symbols of human ingenuity, built on a promise of safety and permanence. So when one fails, it's not just concrete and steel that shatters, it's our trust. In an age of advanced supercomputers and materials science, how is it possible that modern bridges still fall from the sky? The answer isn't simple. It's a tangled web of aging, flawed designs, skimped maintenance, and sometimes the very innovations meant to make them better. Today, we're diving into the world of infrastructure forensics to understand not just what happened in some of the most infamous collapses, but exactly why. A bridge collapse is almost never a single-point failure. It's a catastrophic chain reaction. While an earthquake or a flood might be the final push, they often just expose weaknesses that have been festering for years. Generally, the root causes fall into a few key areas. First, design and construction flaws. Sometimes, the mistake is baked in from day one: a miscalculation, a misunderstanding of materials, or shoddy work on site. Second, deterioration and corrosion. Bridges are in a constant war with the elements. Rain, salt, and temperature swings relentlessly attack steel and concrete. Rust isn't just ugly. It's a structural disease that eats away at a bridge's strength. Third, and this is a big one, is inadequate maintenance. The American Society of Civil Engineers gives U.S. bridges a C+ grade, noting that 1 in 9 is considered structurally deficient. Regular inspections are the first line of defense, but when they're skipped or done poorly, small problems like cracks and rust can grow into fatal flaws. Finally, there is overloading. Many older bridges simply weren't designed for the sheer volume and weight of today's traffic. Constant stress from heavy trucks can cause fatigue damage over time, pushing an already stressed structure past its breaking point. To really understand this, let's look at the evidence from the rubble of 3 specific disasters. First, let's travel to Minneapolis, August 1, 2007. During evening rush hour, a 1,900-foot section of the I-35W Mississippi River Bridge buckled and collapsed, plunging cars and people into the river. The tragedy killed 13 people and injured 145. This bridge was a workhorse, carrying 140,000 vehicles every day. So what went wrong? The National Transportation Safety Board, or NTSB, launched a massive investigation. What they found was a fatal flaw that had been hiding in plain sight for 40 years, since the bridge was first built. The culprits were something called gusset plates. Imagine these as the critical joints in a skeleton, thick sheets of steel that connect all the major beams and trusses. The investigation discovered that several of these gusset plates were only half as thick as they should have been. A critical design error made them fundamentally too weak for the loads they were meant to carry. Over the years, that load had actually increased, with extra layers of concrete added to the road surface. The final trigger? On the day of the collapse, construction crews had parked heavy equipment and materials, weighing over 500,000 pounds, directly over the bridge's weakest point. That extra weight was the last straw. The undersized gusset plates buckled, ripped, and started a chain reaction that brought the entire bridge down. Forensic engineers meticulously recovered the debris and used sophisticated software to create a 3D digital model of the bridge. This allowed them to rewind time, simulate the stresses, and pinpoint the exact moment of failure, confirming the gusset plates were the origin point. Now, let's go to Genoa, Italy. On August 14, 2018, during a torrential rainstorm, a massive section of the Morandi Bridge, a key artery connecting Italy and France, crumbled, killing 43 people. This bridge, completed in 1967, was a pioneer of its time. Its designer, Riccardo Morandi, used an unusual design where the steel support cables were encased in pre-stressed concrete. While innovative, this design had a critical drawback. It made the cables, the most important part of the bridge, almost impossible to inspect. Forensic experts concluded that the collapse began with the corrosion of those hidden steel cables inside the concrete stays of one of the main pylons. The salt-laden air of the coastal city likely sped up the rust, and over decades, the cables weakened until they could no longer support the structure. The storm may have been a contributing factor, but the root cause was this slow, invisible decay. The investigation was mired in controversy, with allegations that warnings about the bridge's poor condition had been ignored for years. The lessons were stark. When you innovate, you must also innovate in how you inspect and maintain. You have to be able to see and assess your critical components. Our third case study is a chilling reminder that even brand new bridges can fail. On March 15, 2018, a pedestrian bridge at Florida International University in Miami collapsed just 5 days after its main span was swung into place. It killed 6 people. This bridge was built using a method called accelerated bridge construction, where large sections are built off-site to minimize traffic disruption. The NTSB investigation uncovered a cascade of failures. It started with a fundamental design error. The designers miscalculated the forces on a critical connection point, making it far too weak for the load it had to bear. This error led to large, alarming cracks appearing on the concrete structure before it even opened. Shockingly, a peer review, which was supposed to be the safety net, failed to catch the error. And when the cracks appeared and began to grow, the engineering team failed to recognize the imminent danger and didn't close the road underneath. On the day of the collapse, workers were actually on the bridge, attempting to retighten steel rods in the very area that was cracking, an action that likely triggered the final, catastrophic failure. The FIU collapse was a total system failure, a failure of design, a failure of review, and a failure of judgment in the face of clear warning signs. So how do investigators piece these stories together from a scene of total chaos? Forensic engineers use an amazing toolkit that combines old-school detective work with high-tech science. After securing the site, they collect material samples and all the documents, from original blueprints to maintenance logs. But the real magic is in the technology. They use something called non-destructive testing, or NDT, which is like giving a structure a medical checkup without harming it. Ultrasonic testing sends sound waves through steel to find hidden internal cracks. Ground-penetrating radar can look inside a concrete deck to map out rebar and detect deterioration. Then there's the digital analysis. Using software for finite element analysis, or FEA, engineers can build a precise computer model of the bridge. They break the structure down into millions of tiny virtual pieces and simulate how it behaves under different stresses. This allows them to replicate the failure sequence step by step, as they did for both the FIU and Morandi bridges, to confirm exactly how the collapse unfolded. The lessons learned from these tragedies are driving real change. The goal is to build future bridges that are not just stronger, but smarter and easier to maintain. We're seeing the rise of new materials like high-performance concrete. It's far stronger and less permeable than traditional concrete, making it highly resistant to water and salt, which stops corrosion before it starts. There are also fiber-reinforced polymers, or FRPs, composites like carbon fiber that are lightweight, incredibly strong, and don't rust. But innovation is a double-edged sword. As the FIU collapse showed us, new designs and materials bring new complexities. If we don't fully understand their long-term behavior or potential failure points, we can trade one set of problems for another. Preventing future collapses requires a culture of vigilance. It means seriously investing in the maintenance of our aging infrastructure, with trained inspectors using the best technology available. It means rigorously testing and vetting new materials and construction methods before they are widely adopted. And critically, it means designing bridges with redundancy. That means if one component fails, there are other load paths to prevent the kind of domino effect collapse we saw in Minneapolis. The twisted steel and shattered concrete of a collapsed bridge tell a story. By listening to that story, by meticulously dissecting these failures, we gain the hard-won wisdom needed to build a future where the trust we place in our bridges is never broken. Thanks for listening to Fun Facts Online.